In this segment, we learned to recognize a couple of important functional groups referred to as the acetal group and the hemiacetal group. This knowledge extends from our basic list of functional groups that we previously learned, such as alcohols, aldehydes, ketones, etc., and expands this knowledge toward these more specialized functional groups. These functional groups are important for a variety of reasons. One of those reasons is that these functional groups are found in a variety of sugar molecules, and hence why we have this mountain of sugar showing up here on our intro screen. Let's go ahead and take a closer look at recognizing acetal groups and hemiacetal groups within organic molecules. So we're looking at acetal and hemiacetal functional groups, which are important to be able to recognize when we are describing sugar structures. We will also encounter these groups as products of some of the reactions of aldehydes and ketones that we'll be covering in later units. So the hemiacetal group we will look at first. The hemiacetal group refers to a group where you have a carbon atom, and that carbon atom is bonded both to an ether group, which I will abbreviate as OR here, where R is a carbon chain or carbon ring, hence making this group an ether because we have a carbon-oxygen-carbon bond. So this top part here we would describe as an ether group. And then additionally, that same carbon atom is also bonded to a hydroxy group. Hence, we would refer to this part of the structure as not an ether, but instead as an alcohol. This special combination of a single carbon atom here that is part of an ether group, and also that same carbon atom is part of an alcohol group, is referred to as a hemiacetal. So hemiacetal is the term that we would use to describe this functional group that we've highlighted in yellow as a whole. All of these components have to be there, and it is absolutely essential that the alcohol group be bonded to the same carbon atom, that blue carbon atom that I'm highlighting here, as the ether group. That is what defines a hemiacetal functional group. An acetal functional group, on the other hand, is structurally similar but has a distinction. That distinction is that the acetal group doesn't have just one ether directly bonded to the carbon, but instead it has two ether groups directly bonded to the carbon here, where R is equal to a carbon chain here, making this whole unit that I'm highlighting with my laser pointer an ether group. And there is also a second ether group directly bonded to this carbon as well. So we would refer to this structure as being a diether because of the fact that we have a carbon atom here that's part of an ether group here, and that same carbon is part of this ether group as well. And so when we have this combination of ether and ether bonded to the same exact carbon atom, we refer to this functional group as a whole. Everything that I am highlighting yellow here, ether, ether, as a whole is referred to as an acetal group. The way that you can distinguish and remember between these two terms is that hemi refers to a state of being halfway. So we are halfway to the acetal group here because we are halfway to having a structure that has two ethers. Let's take a look at applying this information of recognizing these functional groups towards some real-life molecules. This concept is particularly important when we are dealing with sugar molecules, such as so-called monosaccharides, which we will cover in more depth in a later segment. But for now, what we need to be able to do with these monosaccharides is recognize any acetal or hemiacetal groups. So what I'm going to ask us to do in this problem here is for us to highlight or circle all acetal or hemiacetal groups within each of these molecules, where each of these molecules represents a common monosaccharide. Monosaccharide meaning mono sugar, it's a single sugar unit. We will look later on at multiple sugar units joined together to form disaccharides representing two sugar units joined together. So in the structure of glucose, very common, very, very biologically relevant sugar. Taking a look at this structure, When we talk about an acetyl group, remember that an acetyl group is referring to a carbon that's directly bonded to two ethers. So R here is a carbon atom so that we can have two ethers. Hemiacetal refers to an OH group bonded on one side and an O alkyl group, R being a carbon atom here, bonded on the other side. And so keeping that in mind here, looking at the structure of glucose, within the structure of glucose, in order for us to have an acetyl or a hemiacetal group, we absolutely have to have ether or ethers. I've highlighted all those ether groups in green here. And the ether group is the commonality between acetyl and hemiacetal. So to be efficient, what I would recommend we do first here in glucose is look for our ether groups, because those are going to be the possible locations where we could potentially be dealing with an acetyl or hemiacetal group. If we don't see an ether, then we can't have an acetyl or a hemiacetal. Taking a look at glucose, we have lots and lots of hydroxy groups here, 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 here. Here, looking at glucose, I see one ether group. That is, there's this oxygen atom right here. And that oxygen atom connected over to here and to here makes this group as a whole an ether group. I will go ahead and highlight that. That's an ether because we have that carbon-oxygen-carbon bond. Now, in order for this to be an acetyl or hemiacetal, what we have to find is that of that carbon-oxygen-carbon bond, one of those two carbon atoms of the ether is directly bonded to another ether group, or it's directly bonded to an alcohol. In the case of glucose, we only see one ether group in the entire molecule, so we can rule out acetyl because acetyl requires that we have two ether groups. However, with hemiacetal, we look at this, we have an ether group, and we take a closer look at this, and exploring the carbon atoms here and here, when we look at this carbon atom, if this is going to be part of a hemiacetal group, this carbon that's directly part of the ether group would have to be bonded to an OH group. I don't see an OH group directly bonded there. Instead, I see a CH2OH, I see a hydrogen, and then I see a carbon atom, so we come around the ring here. This CH2OH, that OH isn't going to count toward being a hemiacetal because the OH group has to be right here because that carbon that's part of the ether group has to also be part of the alcohol group. So that position cannot not be a hemiacetal. On the other hand, we come to the other end of the ether right here, and this particular carbon right here is directly bonded to an OH group. That OH group is the one that I just highlighted. And therefore, this carbon atom that I've put a red star on would represent part of a hemiacetal group. It would be that central carbon here or here from our functional group, specifically the hemiacetal, because we have a carbon. That's the carbon that I've put a star on that's directly bonded to an OH and directly bonded to an O alkyl group. So in other words, it's directly bonded as part of an ether. So this single carbon that I'm highlighting in our structure of glucose is directly connected to an OH group and it's directly connected to an ether group, making this what we would refer to as a hemiacetal functional group. So I'm going to label that as hemiacetal. We can go through this analogously and take a look at fructose as well, fruit sugar. Taking a look at this structure and orienting myself based on observation of an ether functional group. Our ether is here, carbon, oxygen, carbon there within the 5-membered ring. We have a 5-membered ring because we have 5 points to this shape here. And taking a look at each of the two carbon atoms are two carbons that would be candidates for being part of hemiacetal groups, or acetal groups would be here and here. I've put red dots on them. In the case of fructose, if we come over here, this carbon is not directly bonded to any other O alkyl groups, and it's not directly bonded to any OH groups either. So this carbon cannot be a hemiacetal or acetal. On the other hand, we come to the other carbon over here on the left that I'm highlighting right now. That carbon is directly bonded to an OH group. And so therefore, this group as a whole, where we have a single carbon that I'll put a big red star on, directly bonded to an ether group and directly bonded to an OH group, we would categorize as a hemiacetal. So I'm going to go ahead and label this star as a hemiacetal carbon as well. Within the structure of galactose at our far right here, another common monosaccharide, we see one ether group in this structure as well. It is also part of the ring. We'll see this as a similarity between a variety of these cyclic sugar structures, that they have an ether group in them as a common feature. So within this 6-membered ring, because we have a hexagon here, we have an oxygen atom that's part of an ether. Taking a look at the 2 carbon atoms directly connected there as our candidates for being part of acetal or hemiacetal groups, we have a carbon atom here, and taking a closer look at these, we have on the left a CH2OH group and a hydrogen, and the carbon we follow around the chain. So there's no OH group directly bonded here, so this carbon cannot be part of an hemiacetal group. On the other hand, we come to this carbon, and this carbon that I'm highlighting with my laser pointer right here is part of an ether group, and it is also got that hydroxy group bonded to it. And therefore, we can classify this carbon that I've put a giant star on, again, as a hemiacetal group. So we notice with each of these 3 monosaccharides that they all share a hemiacetal group. And that is common amongst a variety of monosaccharides, not just these 3. Analogously, we can take a look at disaccharides, which disaccharides are structures that have 2 sugar units joined together, such as sucrose, lactose, and maltose, shown here on our screen now. As we look at these structures, we can do the same sort of evaluation and ask ourselves whether they have any acetal or hemiacetal groups as well, as a way of making sure that we're able to recognize acetal groups and hemiacetal groups. So we're asked here to highlight all of the acetal groups and all of the hemiacetal groups. I would take the same strategy here that we did in our last example problem, which is that we take a look at these for the presence of ether groups. I'm going to go ahead and mark my ether groups. There's one here, and I'll try to do these in different colors. There's one here, and highlighted in yellow, there's one that we would say is right here as well. Those represent the 3 ether groups that I see within this molecule. Now that we have recognized those 3 ether groups, what I'm going to do is mark off the carbon atoms that are part of the ether group here, 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 and here. And I'm going to explore each of those carbon atoms to determine whether any of them meet the template for being an acetal group or a hemiacetal, where if they are an acetal group, then the carbon atom needs to be bonded to another ether group, a second ether group. If they're a hemiacetal, then it needs to be bonded to a hydroxy group directly. So looking at the carbon atom right out here on the far right end of the molecule with my laser pointer, this particular carbon is part of one ether group. It's not directly bonded to an OH group, instead it's bonded to a CH2OH, so therefore this carbon atom is not part of a hemiacetal or an acetal group. It is nothing, it's just a general ether functional group there. We come to this position that I'm highlighting with my laser pointer now. This carbon is directly bonded to 2 ether groups, the one in pink and the one in yellow. It's not directly bonded to any OH groups. We would therefore classify this group as an acetal group. So I'm going to go ahead and label that carbon as the carbon of an acetal group. It is an acetal group because of the fact that it has an ether group coming over to here and an ether group coming over here. So you got 2 ether groups directly bonded to this same single carbon, making it a so-called acetal group. And the entirety of the acetal functional group would be represented by not only that carbon atom, but the ether group here all the way through the other ether group would be what's necessary is everything I've highlighted in pink as part of the acetal group. But there's more, because we come over to this carbon atom. This carbon atom is directly part of an ether group here. It's also directly part of an ether group coming this way. So this carbon atom we would also describe as the carbon of an acetal group. And this particular acetal group, I will try to highlight in green here, would correspond to the entirety of that ether group as well as this ether group as well. So this molecule has 2 acetal groups present in it. We come over to our last candidate for an acetal or hemiacetal, that's right here. This particular carbon is part of an ether group, but it's not directly bonded to an OH and it's not directly bonded to another ether, so that does not count for anything. So sucrose we could describe as having 2 acetal groups here and here. I will not go ahead and do this for lactose and maltose But in a later segment, we will be talking about sugars in more detail, and it will be essential to be able to recognize the acetyl groups and the hemiacetal groups in these structures in order to understand how monosaccharides with one sugar unit relate to disaccharides with two sugar units, and then polysaccharides with a large number of sugar units joined together.